Understanding data types in Python. So we have renamed a new file by understanding data types in Python. So effective data-driven science and computation requires understanding how data is stored and manipulated. So this lecture and furthermore lectures outlines and contrasts how arrays of data are handled in the Python language itself and how Numpy improves on this. Understanding this difference is fundamental to understanding much of the material throughout the rest of the course. Users of Python are often drawn in by its ease of use, one piece of which is dynamic typing. While a statically typed language like C or Java requires each variable to be explicitly declared, a dynamically typed language like Python's skips this specification. Okay, let me show you an example. For example, in C, you might specify a particular operation as follows like this. As you can see, if you have learned or you have some understanding of the C language, you can see that it is a particular operation. But in Python, while in Python, the equivalent operation could be written this way, like this. Okay, so notice the difference. In C, the data types of each variable are explicitly declared, while in Python, the types are dynamically inferred. This means, for example, that we can assign any kind of data to any variable. For example, let's remove this. X is equals to 4. X is equals to like this. Here we have switched the contents of X from an integer to a string. The same thing in C would depending on compiler settings, to a compilation error or other unintended sequences. For example, the error which will fail to run this, although it will depend on the compiler, but it will usually give the error like this, which is in C. So this sort of flexibility is one piece that makes Python and other dynamically typed languages convenient and easy to use. Understanding how this works is an important piece of learning to analyze data efficiently and effectively with Python. But what this type flexibility also points to is that the Python variables are more than just their value. They also contain extra information about the type of the value. We'll explore this more in the upcoming lectures as follows. Okay, so now let's start. A Python integer is more than just an integer. Okay, so the standard Python implementation is written in C. This means that every Python object is simply a cleverly disguised C structure, which contains not only its value, but other information as well. For example, when we define an integer in Python, such as x is equals to 10,000, x is not just a raw integer. It's actually pointed to a compound C structure which contains several values. Looking through the Python 3.4 or 3.7, 3.6.2 source code, we find that the integer long type definition effectively looks like this once the C macros are expanded like this. A simple integer in Python 3.4 or 3.6.2 or 3.7, which is the latest edition, actually contains 4 pieces, which are okay, number 1, which is ob underscore refcnt, which is a reference count. So a reference count that helps Python silently handle memory allocation and deallocation. giving the spaces so that it is easy for you. OB type, object type, which encodes the type of the variable. Object size, which specifies the size of the following data members. Object digit, which contains the actual integer value that we expect the Python variable to represent. Okay, so this means that there is some overhead in storing an integer in Python as compared to an integer in a compiled language like C. As we can see here, so there's a difference between C and Python integers. As you can see here, C integer, and which is Python integer digit 1, Python object head. So here, this one, py object underscore head, is the part of the structure containing the reference, count, type code, and other pieces mentioned before. So notice the difference here. A C integer is essentially a label for a position in memory whose bytes encode in an integer value. A Python integer is a point to a position in memory containing all the Python object information, including the bytes that contain the integer value. This extra information in the Python integer structure is what allows Python to be coded so freely and dynamically. All this additional information in Python types comes at a cost, however, which becomes especially apparent in structures that combine many of these objects. So, moving on further, we will now discuss a Python list is more than just a list. Okay, so let's consider now what happens when we use a Python data structure that holds many Python objects. The standard mutable multi-element container in Python is the list. We can create a list of integers like this. Let's start. L is equals to list range 10, which will give the answer. Sorry, I forgot L. It gives the answer 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So now we will write type L. We want to know which type is this. 0. That's an integer type. Or similarly, a list of strings like this, we can write L2 is equals to square bracket str, the bracket C, for C in L, L2. Okay, so let's see. Here it is in the string formation, and we want to know the type, which will result in string, I guess, and it must be type L2. Sorry, here we use the brackets L2. Now we will use the square bracket 0. We want to know, and we will. Okay, so now it will be str, which represents for string. Yes. Now let's go for L3. True. Double quotes. 2. 3.0. 4. Type. We want to know the type, so we will write type. The bracket item for we put the bracket for now item in L3. Let's see. So So the first one is bool, boolean, then the string, then float, and then integer. So because of Python's dynamic typing, we can create even heterogeneous lists. So but this flexibility comes at a cost. To allow these flexible types, each item in the list must contain its own type info, reference count, and other information. That is, each item is a complete Python object. In the special case that all variables are of the same type, much of the information is redundant. It can be much more efficient to store data in a fixed type array. So the difference between a dynamic type list and a fixed type list, which is the Numpy style array, is illustrated here. So that's the difference between C and Python lists. At the implementation level, the array essentially contains a single pointer to one continuous block of data. The Python list, on the other hand, contains a pointer to a block of pointers, each of which in turn points to a full Python object like the Python integer we saw earlier. So again, the advantage of the list is flexibility because each list element is a full structure containing both data and type information. The list can be filled with data of any desired type. Fixed type NumPy style arrays lack this flexibility but are much more efficient for storing and manipulating data. Okay, so here you can see the difference between C and Python lists.